We're moving on to the dynamics portion of the course. So basically how it works is, oh, by the way, with your marks and stuff, if you'd ever like to talk to Wei or want to remark or anything, his office is in level 6. Probably send him an email first if you're looking for that sort of thing. With a remark, how it works is he will personally remark your paper, and if it's a higher mark, you get the higher mark. If it's a lower mark, that's your mark. You know what I mean? So it's a risk to get a remark. Okay, one more thing I want to say. One second.
What do you do?
So yeah, in my Google Drive folder, basically, I think I brought this up just before the test in week 5, but if you want to read through my creation, this is the Sigma Bible for this course. So if you ever need course notes and stuff, this is all, you click it, it's hyperlinked, all that stuff. I was basically just practicing writing my thesis up using this program called LaTeX, which has like the really nice formatting and like hyperlinking. And yeah, I did this as like a little fun project, right? Anyway, so yeah, that resource is there if you need it. It gives you additional like questions and stuff that you can go through. That stuff is also available in my Google Drive, right? Okay. So in terms of this course and how it's structured, you've seen me pull up this like pretty much every lesson. We've moved away from statics now. We're going to dynamics, and here's where we would really utilize the second law. So that's F equals ma. That's when things are moving, basically. Let's consider the mass and acceleration and things like that. And specifically, we're going to be focusing on particles. I believe. Okay, basically, I'll tell you the scope. Your midterm will include everything within this region, so just particle dynamics, right? Rigid bodies, and specifically rigid body kinematics, is going to be in your finals, as well as some more difficult stuff to do with frames and all that. Rigid body kinematics will be in your finals. It'll be what we're covering in week 10, alongside some more frames. But kinetics has, I don't want to guarantee this until week 10, but kinetics has been kind of like not included in the finals, so it's essentially not accessible content based on the civil school and how they run 1300. In all the other schools, you know, mech, mining, they run kinetics as well, but it's one of the more difficult parts of the course and they've slashed it out. Not to say that kinematics isn't hard either for rigid bodies, but at least one part of the difficult part of this course isn't in it anymore, you know what I mean? So yeah, we're going to be focusing on particles, right? Okay, so here, this is like a kind of like tree diagram, which, I don't know, this is based on what I wrote when I was teaching it for the mining school. So again, this part isn't really relevant to the civil school, but I just like to categorize things like in this tree diagram kind of way, and I'll give you a summary of what to expect, I guess, especially for this portion, which is what we'll focus on today. So there's quite a bit of content you can see. And again, all of this is in your midterm, which is in week 9. So I'm trying my best to do this today, and then on Friday next week, we'll be covering the kinetics portion, right? Oh, sorry, and that includes impulse and momentum. I should put that here, actually. It's probably more accurate. That's the way that I would see it. Okay. So, kinematics and kinetics, right? So we should understand the differences between these words. Kinematics is basically concerned with how a particle travels through space, such as its displacement, which you'll find is s with a little hat on top of it, indicating that it's a vector. V, which is velocity of the particle, and a, which is its acceleration, right? So you should be relatively familiar with these concepts just from doing Phys 1A, but yeah, obviously it helps if you've done physics in high school and stuff like that, right? But yeah, it's all right. I'll try my best to explain it and pace through this workshop at a decent speed. Basically, kinetics will use some. Basically, kinetics. It's about indirectly finding forces and motions using Newton's second law. So usually kinetics you associate more so with Newton's second law. These ones you find the positions of the particles, its speed, acceleration, but we don't really concentrate on the forces so much, which cause the particle to move like that, right? Indirectly finding F and motion. So for kinetics, we don't really care where the... Oh, sorry, no, that's not an accurate way of saying it. Okay, yeah, basically it's a complicated topic. I'm just going to keep it at that so that what I'm saying is still true. You know what I mean? Okay. Rectilinear motion is just a really fancy way of saying moving in a straight line. This is straight line motion. And that includes going backwards on that same line. So you can think of like 1D number lines and stuff like that in like maths. Yeah. Okay, next we have 2D particle kinematics. So we're going to be talking about 2D coordinate systems. There's a couple which I'll run over in like the second part of the workshop. By the way, this workshop, I'll obviously give you a break still, but we won't have time for like quizzes and stuff like that, sorry. So yeah. I'm just going to draw it like projectile motion. Here's an example of 2D particle kinematics. Like a ball or whatever travels throughout the air. This is like a 2D coordinate system, right? X and Y motion. You can also have relative motion. So like, for example, a plane is flying this way, like due north, and then another plane is flying like due west. What's the relative motion to each other? That's another concept that we can explore in a 2D coordinate system. And curvilinear motion, right? That's motion in a circle. We'll talk about centripetal forces and stuff like that, right? Okay. So yeah, I might not cook up the rest until next week, but yeah, we'll leave it at that for now. Yeah, okay. Does anyone have any questions with what we're going to be tackling today? Yeah. So the basic motion quantities that we're going to be dealing with are displacement, velocity, acceleration, right? Denoted by S, V, and A, as I mentioned. They have units meters per second, and meters per second squared. And they're also derivatives and integrals of each other, and here's how the layers work and stuff like that, right? Okay. Basically, we're going to be solving particle rectilinear motion, straight line motion in this way. Considering these motion quantities, and we're going to be using a little bit of our understanding of calculus to do so, right? So usually in this part of the course, you either are given a function that's like a, what's the word for it? Like algebraic expression, right? And then you're told to find various numbers associated with these motion quantities. So yeah, basically the two methods which we'll be covering is the initial conditions method, right? So initial conditions will help to solve for those integrals, right? Which have like the plus C thing for indefinite integrals. And separable ODEs method, I'll show you what that means. But basically we'll be dealing with definite integrals instead. And there's a lot of implications in this part of the course. Like for example, sometimes when we're dealing with gravity, it's implied that gravity is 9.81 meters per second squared going downwards, towards the Earth. These are things that are implied, right? But you have to learn all the little tricks. There's a lot of niche cases and stuff. Oh, not really niche cases. There's a couple of general rules, such as gravity, which you have to look out for. And that just comes through doing a lot of practice, right? Okay. Probably help, like I've included the separable ODE method if you want to look through this later, but it helps to just see an example of the separable ODE method. But before we do that, I want to just go over the initial conditions method. To me, it's a little bit more intuitive. Sorry, just so I can see your faces. Yeah, the initial conditions method just seems a little bit more intuitive. You have the integration constant, find values to plug it in, right? But separable ODEs I find are easier when the expressions become a little bit more difficult to deal with. You start getting your higher order equations like parabolas and stuff like that, and cubics and stuff. Okay, so here's the first question. Basically, there's a lot to absorb. Let me just get it up. So it says a particle starts from displacement is equal to 0. So that's just like 0 on your coordinate system, and travels along a straight line. That's rectilinear motion, right? With a velocity of, they give you some algebraic expression for the velocity, where t is in seconds, right? Construct the s-t means displacement versus time graph, and a-t means acceleration versus time graph, right? And the time interval that we care about, so on our graph, our domain will be 0 to 4 seconds, right? They've given you the graph for velocity over time already, and I mean, outside of the question, you have to like kind of zoom in, squint your eyes, and realize this has some information in it as well that we'll need later. Oh, I mean, actually, they gave you the function already. So this just visually represents what's happening. But yeah. Okay. So the first thing is the acceleration, right? If we look at, sorry, I know some of you guys are copying this down. I'm just going to scroll up for a second. So basically we started here. So we started at the acceleration function. In order to get to acceleration, we started the velocity function. In order to get to acceleration, we have to derive it. And then to go the other way, in order to get to displacement, we have to integrate it, right? So these are our basic rules for when we're solving particle rectilinear motion of like these functions and the motion, right? Okay, so basically, we have to derive this equation. T squared minus 4t plus 3. That's what I've highlighted in blue. That's what we're given in the question, right? Okay, and then yeah, most of these are just polynomials, right? Most of these questions you're going to be given. So yeah, we're all good with calculus and deriving polynomials. It should mainly stick to polynomials. I've only ever seen one, which is like the natural log one or whatever. Yeah. I'm really bad at maths, by the way, so get ready. There's no way you guys are worse than me at maths, so yeah. Basically, this is our function that we're going to roll with for acceleration, right? And then for displacement, we go the other way around, right? So we're going to integrate. Oh, what have I done? I'm going to do it as an indefinite integral. In my notes, I've written it as a definite integral. But yeah, so that's our equation again. And when we go the other way to integrate, you get this. Yeah, don't lose aura by not including the c. So always include that integration constant c if you're doing this method, right? Okay. So now we have to solve for c. So basically we're told this additional information, particle starts from s equals 0 when time is equal to 0, right? So when t is equal to 0, s is equal to 0, so therefore c is equal to 0. The way you do that is you plug in 0 for your s, plug in 0 for your time, right? And then, yeah, once you figure out that c is equal to 0, yeah, you just plug it in like that. So I can undo that. I'll just scratch that out. That's 0. Right? Okay, so now we have our equations that we're going to roll with for acceleration and displacement. Now we're just going to graph them, right? So we'll graph the orange one first. That's acceleration. Sorry. That's this here, right? Okay, so this is going to be a linear equation, right? Straight line. So y equals mx plus b, this kind of thing, right? So b is -4. That's our y-intercept here, right? and it increases at 2 per second, and we care about it until t is equal to 4, right? So when t is equal to 2, it's at 0. Yeah. Here it goes up to 4, right? So we're basically just linearly increasing our acceleration from -4 all the way to 4. Yeah. Okay. Next, for... Oh, sorry. Why have I drawn the V graph here? The V graph is this one, right? This is what we... I think I just drew it anyway for the lols. Just duplicate it. I think I just drew it to show you, I guess, like what the graphs look like stacked on top of each other. Yeah, so we'll just draw that quickly. Right, 4 seconds. Oh, sorry, yeah. You can actually look here, it already gives away the answers, right? So 3, 1, and 3. But you can solve this using subbing in when v is equal to 0, stuff like that. Yeah. And then finding the x-intercepts on a parabola, right? Okay. Okay, so lastly, our displacement function is going to be a cubic, right? Copy it down. Okay. I like using like kind of the same logic as we've been using for like shear force diagrams and bending moment diagrams. Basically, the points of 0 velocity on a displacement graph will correspond to flat slope, right, on an acceleration graph, right? So basically, it'll be rising, and then it'll have a flat slope at 1, right? And then it'll be falling, and it'll have a flat slope at 3. So here's your point of max inflection, right? Oh my god. Oh my god. Anyway, yeah, you know what I'm trying to do, right? Okay, and then, yeah, it'll finish like this. So to get these exact numbers, we can look for the t-intercepts using this formula, right? So let's look for the t or the x-intercepts, right? So we simply set all this stuff equal to 0. So right, this will check for where it intercepts our our x-axis, which is our time, right? We pull out t. We pull out 3. Sorry. We pull out. Yeah. Anyway, you bring out all that stuff. 3t comes out the front, right? And then, so we've just simplified the equation, and you get this, right? So t is equal to 0, because for this one, this is when t is equal to 0, as well as t is equal to -3 and t is equal to 3, right? Which is from our perfect square or whatever it's called. I'm so bad at maths, I'm sorry guys. I don't know how to explain it, I just know how to do it, you know what I mean? This is like later in this tute, like you'll get a better explanation once it's like back to physics, but right now it's just maths, and I hope you can do the maths better than me, basically, right? So we're just solving for the t-intercepts, right? So there's 3 essentially, and the ones that we care about is 1 and 3, like that. Okay, and then maybe we also want the key values for s, right? So let's say we don't know what the values for s are at 1 and 4. So we can just plug it into our equation. So when we plug in 1, we just, like, time is equal to 1. It'll look like this, right? Yeah. When you solve for all that, you get 1.33 meters, right? So that value here is 1.33 meters. Yeah. The other one is S is equal to 4. So let me just rub out the ones. If we plug in 4 instead, you're actually also going to find it's equal to 1.33 meters. Sorry, I've just, instead of writing it out again, I just, because there's not much space on this page. But yeah, that one's also 1.44 meters here. 1.33 meters rather. Yeah. Okay. Is that all good? Okay. Okay, so next we're going to do the separable ODE method, right? And I'll run through the steps for that. But real quick, so we're throwing this ball outside of like a window of a building, and there's no wind and stuff, and so the ball's motion goes straight up and down, right? Is this an example of rectilinear motion?
Yes.
Very good. So even though the ball, right, if you map it over time, it's going to form a parabola. The idea is that its motion is only one-dimensional because we don't consider wind and stuff like that. Right, yeah, question.
So, can you go back off one?
Oh, yeah. Yep, okay. So this question is asking for a few things. The ball is thrown upwards with a velocity of 10 meters per second from window, and it's 20 meters above the ground, right? The ball experiences a constant acceleration of 9.81 downwards. So this is what I'm talking about with gravity. But in some questions, they won't even include this sentence. It's just kind of implied. If you see a building, that gravity, if you see a building and you throw a ball upwards, it's implied that gravity acts on the ball, right? Okay, yeah. And then, so what's the maximum height the ball reaches? What is the speed of the ball at this moment, and when does that occur? And when does the ball hit the ground? And draw a displacement time and velocity time graph for its motion. Okay, so let's go through this method. So we're going to use the separable ODE method, which is a way of using definite integrals to solve these kinds of questions. So we can start from acceleration. We know that acceleration is also equal to dv over dt. And with the separable with the separable ODE method, we can almost consider this like a fraction, even though it's an expression of derivation, right? So what we're going to do is we're going to separate dv, or all the v terms onto one side, and then all the t terms onto the other side, right? So basically that looks like this. I've literally just multiplied dt onto the other side, right? So we're treating this as if it's a fraction, right? Then we slap an integration symbol onto both sides, right? Remembering that this is just a constant, right? Negative 9.81 is just a constant. And okay, here's basically for the upper and lower bounds of these definite integrals. Usually for a question like this, it's implied that you start at t is equal to 0 and, sorry, not v is equal. And we're told that v is equal to 10, right? So this is the initial velocity, right? So this is going to make up our initial portion of these variables. So because the initial velocity was 10, we're going to put that as the starting integral bound on the velocity side, right? And then we just imply that time starts at 0, right? Then over on this side, this is the initial time, right? Okay, next we're going to set our final time, or like our our integral bound, our upper integral bound, as an unknown. So the unknown we're going to set it as is v on the velocity side, and t for the time side, right? Once we solve these, you get v. So you can kind of pretend that if there's nothing on one side, that there's a 1 on that side. So the constant there is 1, and the constant here is negative 9.81. So it's negative 9.81, t, and then 0, right? So we haven't like resolved these integral bounds yet, but we will. So this one will be you sub in v for the upper integral, and then sub in t for the lower integral, right? So, and this one's t, and then it's minus 0, so that part disappears, right? Okay. And then we just solve for v, right? So we simply move t onto the other side, and there we go. That's our formula for t, right? A shortcut. Actually, you know what? I won't go into it at the moment. I'll go into it in the next part. So yeah, that's all good. Okay, but now we know that so now we're going to solve for displacement, right? And we know that v is ds, which is displacement, right? ds on dt, right? And we're going to do the exact same thing. We're going to separate and then integrate, right? So we're going to multiply dt onto the right-hand side, and then we run into this again. Sorry. Right, so, and then we just slap the integral onto both the left and the right side. And now we have to find the integral bounds, right? So let's look at our question again for the left-hand side. We're told that the window is located 20 meters above the ground, right? So that implies that our initial condition for displacement is 20, right? Because we start 20 meters away from our reference point, right? Which is the ground, right? Okay, so we chuck in 20, and then again, we're going to set the upper bound of that integral as an unknown that is variable. So this will give us our function, right? And then again, the initial time is 0, and we're solving for our unknown time, right? So, sorry. Basically, I'm going to skip an extra intermediate step here, but you're going to find this s equal 20, and then negative 9.81 t squared on 2, and add on 10t, right? When we move the 20 onto the right-hand side, we get this. Okay, so now that gives us our expression for displacement. Okay, any questions with that? So now we've basically found out what our functions are. So now we have to just, I guess, like utilize these functions to find what the question is asking for. So it's asking for stuff like what's the maximum height the ball reaches, what's the speed of the ball at this moment, and when does it occur, right? So this is one of those implied things. This is a part of, I guess, projectile motion, right? Can someone tell me what is the speed of the ball at the moment it reaches the top height? Very good. So at the apex of a throw, the velocity is 0, at least the vertical velocity is 0, right? Like going that way, right? So it's basically just saying v is 0 meters per second, right? So it's not moving up or down. And then we have to find what t is, right? And we have to find what s is based on this information. So, I didn't rub this out. Maybe I'll rub this out. Sorry. I like to basically rub out rub out parts of my note and then fill them in, because then we can do it one step at a time. You're not looking at like 5 lines of working at a time. Okay, so we know, at the apex of a throw, velocity is 0. We don't know what the time is. So we have the most information from our velocity formula, right? Which I'm just going to copy over. Like that. We're just going to sub in 0 for velocity. And now we can solve for t quite easily, right? So we've just divided 10 by 9.81. This is our time until we reach the apex of the throw, right? And using this information, we can plug into our displacement formula. Yeah. So we're going to plug it every time we see t. We're going to plug in 1.0194, right? Let's just do that. 1.04. 1.0194, right? 25.097 meters. So this is the max height that the ball will reach, basically, right? Yeah? Okay. The next part of the question, B, when does the ball hit the ground, right? Okay, so basically, the information that is known from that, okay, let me just, we started at a height of 20, right? We know the function to track the position of the ball, which is our S function. So we just need to plug in when S is equal to 0, right? So 0 is when we touch the ground, right? And we're going to replace this left-hand side by 0 with 0. And yeah, you can see that this is a parabola, right? So you can solve this using the quadratic equation. Yeah, it gives you this essentially, right? I mean, yeah, obviously we're going to pick the positive value, but if you're interested in graphing it, right? So we're doing this one, right? It's just on the next page. Oh, it is on the next page. Sorry, I'll just show you what it is below. Let's graph S, right? It's going to look like you start at 20, you end over at 0 you end at 0 at t is 3.28, right? It reaches the max height here and then reaches the ground like that. The max height was, what did we find? 25, right? And basically that additional value was basically when t was negative, right? So that's why it was a parabola and it gave a negative value. Okay, let's also graph v, which is our speed, right? So v is a linear function here. And we care about v up until it hits the ground. We don't really care about how it bounces and all those kind of effects, right? So it hits the ground at 3.28 seconds, right? Oh, I didn't draw this very well. And at the peak of the throw, right, it had a speed of 0. And that time that we found was 1.0194. And it started at 10, which was our initial condition that we were given, right? So this is basically all we need to know about the throw of this ball, or like the motion of this ball as it's thrown, right? That's, yeah. Okay, does anyone have any questions? Okay, so that essentially, those two questions essentially cover most of what can be expected in rectilinear motion, right? So you can either use the initial conditions method and the separable ODE method. I prefer the separable ODE method. It's a bit more step by step. The other ones just do random shit until it works. But yeah. Yeah, okay, I'm gonna give you guys Smoko for like 10 minutes and we'll come back at 5 and then we'll cover 2D coordinate systems and stuff like that. I'll leave the screen on this and you can have a look at it if you want, but we won't talk about it until after the break. If anyone came into the room, like, yeah, you're looking for your exam paper? Yeah, just come up the front if you're looking for your exam paper. Your name was? How do you spell that?
LECHE. Last name is One more point. One more point. Oh, come on.
Yours doesn't have a mark in front, but I think you can see it on Moodle.
You have a unit?
Oh, sorry.
I just have to get that one right. I made all these assumptions.
Yeah.
I need one last one. Yeah, I think all of us.
Brad Pitt's. Got that.
One.
Yeah, but I did engineering.
Already.
Oh, what were you doing in engineering?
Come on, I didn't get like a.
Sorry, that's the only Aiden I have. You sat the exam in my room, right?
Bro, I rolled. I was like, so close.
Sorry.
Normal then,
Bro, surely is that not my unit?
I'll look for the last time.
Are you trying to get an 8? Is that why you need the extra one mark?
Wait, it's like, if it's 85, but it's 84. Come on. It's like you get it 49. Yeah, no, that's the word.
Yeah.
When I had
49.
49, 42, 5, I was like,
You're not Ting Ru.
Oh yeah, that's.
Oh, sorry, yeah.
Yeah, that was like literally like the way.
Sorry for your loss.
Yeah, good marks.
it was almost like not take 3 classes, just can't be yours.
Yep, good name.
I had to do that. Oh no, I didn't. I had to do that in one of the questions to like get the pass.
Just go to 0.
You knew it was like the next percent is going to be like the same as that answer. So zeros. Or if it's a negative answer, 0 to 1.
So it's like anything multiplied.
Anything multiple, that's 0.
Oh, gee.
I mean, it's good, but it's bad.
I mean, marks you down for you like rounding the wrong way.
Is your mark missing?
Yeah, you lose points.
so
You lose points.
you can
Then
see
you get
your
error
mark
code forward,
right?
right?
Yeah, so
You get 66
Yeah, definitely.
for a question.
yeah, you were like one of the 2 people in my class who didn't get a
Or you
mark.
can't really
But you got it marked on the right?
get like a
If you want a like more specific mark breakdown,
just get
mask plan.
Oh, I hate that. Like,
Because I don't know why they gave you a mark probably on middle,
Yeah.
but then
because
it's not marked. You know what I mean?
Yeah.
Yeah, yeah, sorry, yeah. But you can just keep it and stuff, right?
They're not there.
yeah,
Whereas on one of those tests,
no way.
if you go to do it like certain
Yeah, it's like going for your driver's license. It's like the L's test.
and you just go to the last question wrong, it's like GG.
It's over.
Yeah.
Or like the math exams, bro. I always find like the
What
math
choice?
is-
Yeah. Yeah. I mean, the driver's test funny. You just no one actually.
No one raises their hand to like see.
You just do it. Most of the actually.
Yeah,
It's gonna be shiny. To 2 tries back. Take more than 3 tries.
Right.
3 tries. Probably hours there. I mean, even you got to eat.
These is like just drive around. You can stop at any point during a piece and just like wait.
Is that right?
You're allowed to just pull over.
And they can't fail you for
They
that.
can't vote. It's taking you into a dangerous situation. Don't do it. Just do the thing.
Yeah, they're going to just hate you. And just
Yeah.
like try to tell you something else.
But you can just pull over and wait like 2 minutes.
Yeah, but then if they do fail you for something else that's like kind of fabricated, trying to say, well, they were just speaking for just against me because I went to there's lots of time down and just
But like, but they can just say, oh, this guy missed 3 headshots. How are you gonna prove that wrong?
True.
Yeah.
How are you gonna prove it wrong?
get a dash cam in the car.
Just get like the 3-point turn instead of the reverse parallel button.
I think I actually messed my curves up when I got the reverse parallel. I was like,
Yeah.
I don't think it's sad. I don't remember. I don't
Just
think.
too much of the wrong thing.
Yeah, literally. Yeah. I can't believe they do a 3-point turn like on the same level as the reverse parallel.
Yeah.
Some people to this day still can't do a reverse.
I had to like figure out how to do it because I do pizza delivery like for work, and so like sometimes when you park in, there's nowhere to park. So I had to like, I was like, shit, I haven't done it in years.
Like, where do you do deliveries?
I live in a Goodall Park.
Oh, true.
Yeah.
But you just serve Domino's or something. Or is that
Yeah, like a local pizza. Yeah, place. It's
But
just-
no, when you work for a local pizza place, it's the best. They actually do you get like a delivery bonus? And
yeah, all that shit.
good day. I used to do it back home. I used to that's like $70, get like $40 to $50 an hour
Hell
quick
yeah.
enough, and I was like, yeah. And then when you get like a $25, and then you hear like the Domino's drivers, they just like,
Yeah,
they earn
terrible.
$16 an hour. No tips. Everyone just hates it.
Yeah.
And then there's like 8 people and like 8 delivery drivers. So
Yeah.
they do like 10 deliveries or not.
Yeah, Jenny would like to go.
You gotta do it at a local one.
Yeah.
And then it's fun.
Yeah. Yeah.
How big's the area that you do it in?
Pretty big. We do the entire suburb and then down like the neighbouring parts too. So sometimes I have to go out to Indian Plains, which is across the Japan River. Sometimes I have to go and there's like this rural area that's like just below. Or there's like 2 towns that are like far away. Those ones are good. Like it sucks that you don't get to like do as many deliveries, but you just like drive out and like do a couple like half an hour or something.
Yeah, and then sometimes they'll be like, well, you have to come pretty far, we'll give you extra tip, like, extra money, like, deal or something like that. Big tip delivery.
It's crazy. I didn't realize people like tip that. Like some people tip. Some of them is like, you're heaps so there's no way. Why are you tipping like cash? Like I had one dude, like obviously or something like that. It's like, oh, it's hard times, it's hard times. He just gave me like, he gave me $20. Just cash. He's like, oh, don't worry about the change.
Yeah, how did that happen?
Yeah, it was good, but it was like,
One of my mates was working with. It's like, I pulled up to this house party once, and there was a like it was like a hands party, and the girls came out. They're like, "Oh, if you stand naked, hey, we'll give you $50."
$50.
Yeah, and so he just went in there and started dancing. I mean, easy money.
Yeah.
And just so many times, just like tips, like $40.
Yeah, that's
That's like an hour. More than an hour work. But it's just working at a restaurant.
yeah.
Like no one's giving tips, and then the tips you get like the staff like get like split. So the dish you get never gets any.
Just give me $20, give this the dishwasher.
Yeah, like the tips get split at Christmas, and then it's like somehow the dish you get $10, whereas everyone else gets a couple hundred. It's like, I make your dishes twice.
It's the worst job, like when you're stuck on dishes.
I hope that no one our age is stuck.
Sometimes, like when I'm closing, doing all the deliveries, because it'll be like Tuesday, they'll only be me and like 2 other people. I just close and you end up having to That's different. I'm not doing dishes the entire shift. That's like mainly something.
No, but it's the worst when we used to have like a small shop, so they would used to not roster on the dishes, so you might do deliveries and you see.
So, yep, we're just gonna return we're gonna return to the sheet. Okay. So basically, I might rub this out. Sorry, 1 second. All right. Basically, in 1300, you're going to see different 2D coordinate systems, and when I'm talking about 2D coordinate system, I'm talking about something like the XY plane, right? So obviously, no third dimension, no like Z direction or whatever. And you'll also see NT being the normal tangential plane. So normal tangential plane is useful for when you have motion on inclined ground. So you're seeing stuff like that. Oh, actually, I might go through in order. So XY motion, you'll see this used when you have motion on flat ground, like this, for example. And you have someone like pulling it or whatever. Projectile motion, I mean, we've gone over a one-dimensional projectile motion question, essentially. It's just that vertical throw of the ball off of the building, right? But in 2D, you'll see it goes like that. And we're tracking the ball's motion in those 2 dimensions, the y dimension being the direction of gravity. And relative motion, yeah, you have like plane flying due north or something, and you have another plane flying like due east, and all that stuff. So that's relative motion. Relative motion can, be in the context of things other than, planes, boats, and like cardinal directions, but that's generally how it's presented. Yeah, and then for the NT plane, it helps when you're solving questions which are to do with motion on flat ground. When the ground's inclined, basically, looks like this. Right. Generally, it helps to solve everything in terms of this normal tangential plane, because the first step in solving these kinds of questions, we'll get into more detail about this next week, is, like the direction of the weight, right? That's mg, which is pointing towards the earth. And then we have, sometimes you have friction, right? Sometimes you have the direction that's being pulled, or it could even be inclined like that. And normal force is always perpendicular to the plane, right? So usually you go mg to n to friction slash, to friction, let's just say, right? So yeah, it helps with the unknowns, which are generally like n and f, to break things up in terms of taking the sum of the forces with respect to the normal and tangential directions. Sorry, that was a mess. And curvilinear motion. Let's see if I have a drawing for it. So you're tracking a particle's motion, right? You're going to have acceleration in the tangential direction, tangential to the circle, and normal to the circle will be our centripetal acceleration, right? I want to quickly say, this is a realization I made just now in the break. The motion on inclined ground and flat ground, generally this is to do with Newton's second law, which is like, sum of the forces, that kind of stuff. Every time I look up the definition of kinematics and kinetics, I get confused, but I'm pretty sure that's kinetics. I'm pretty sure whenever we deal with the forces stuff, right, it's actually next week's topic. Right. What we really care about for kinematics are like when we're just tracking the motion, like without respect to the forces, right? But I'm just giving examples ahead of time, I guess, on like coordinate systems, right? So these are the kind of coordinate systems you'll see next week as well, right? Okay. Another one you'll see in the mining school or mech school is polar motion. Long story short, you don't need to know it, but sometimes you have like a satellite that's tracking a rocket's motion, and it helps to track it in terms of a radial direction and angular direction. And also helps, if you're programming like a robotic arm that has like that's like spinning around and it's oscillating its, hand part like that. It's like sinusoidal motion. Yeah, that's polar motion, but we don't care about it in this course, basically, right? Sorry, in the civil school for this course, right? Okay, does anyone have any questions to do with those concepts? Okay. So yeah, again, I've included this, but this is technically a part of next week. It's kind of weird, right? So the way they generally teach dynamics or particle dynamics in this course is they like to teach you about Newton's second law for very basic cases first. So, you're taking some of the forces for, incline and flat ground and that kind of stuff, and you have friction involved and whatever. But that's technically kinetics, right? But kinetics, there's more to it than just Newton's second law. Like kinetics, we're going to deal with work energy methods and impulse momentum methods, right? And for kinematics, which is what we're kind of going over today, we have our 1D and our 2D stuff, right? So 2D is what we're going to go over soon. 1D was our straight line motion, etc. I've sort of taught it like this, where we're going to go over 1D and 2D I read the same thing twice. Kinematics. I'm going to teach it like 1D, 2D, and then go back to this stuff. But, some textbooks, some courses, they like to teach it this one first, and then you move on to kinematics, you jump back to kinetics, and do like those work energy methods and impulse momentum methods. Do you know what I mean? So it's like, that's why I think the words kinetics and kinematics always get mixed up, because the order in which it's taught is usually kind of just back and forth, you know what I mean? Anyway. So yeah, this is basically part of kinetics, so, and this one as well. So we'll talk about that next week. Projectile motion, right? Here are the formulas I would use for projectile motion. It's just an extension of what we kind of did in question 2 there. Essentially, these are those like hidden values which are implied. It's that the vertical acceleration is due to gravity, and the horizontal acceleration, we don't account for like air resistance and wind and stuff like that usually. So we just say that the horizontal acceleration is 0, right? So it doesn't, it just stays a constant speed when you fire a ball out of a cannon or whatever, right? Okay, here's something which I like to keep as like a kind of rule of thumb. The function is your initial plus your change component, right? So this is like, okay. Basically, your function for velocity is going to be your initial velocity plus the change in velocity, right? Acceleration is like dv dt multiplied by time, right? So I just call it acceleration multiplied by time, right? So in the horizontal direction, that's 0. So essentially our horizontal velocity is just equal to our initial velocity. That's just set. So as you fire a cannon, like a cannonball out of a cannon, that speed just stays as its horizontal speed the entire time, right? And when you integrate that, it's just multiplied by t, right? Because we've integrated with respect to time. So we've done a definite integral where the c is cancelled out essentially, right? Because we're starting at t is equal to 0 for my simplified formula here. And for the vertical velocity, right? We take the vertical component of that speed, but now we have to account for gravity changing it, over time, right? So yeah, and then when we integrate that, we have to also account for that component, right? And so, that just becomes a higher order essentially, right? Okay, hopefully that makes sense. These are general like formulas which will keep coming back when we're doing projectile motion questions, essentially. But it's all derived from that idea of function is equal to initial and the change component, like the initial component, the change component. Okay. Oh, and sorry, usually the initial component, right, these ones, is based on, like, you know, your cannon or whatever, for example, we're firing, usually given this angle, or if you're not given this angle, you have to solve this angle, and then you can break it up using your force components that we've kind of talked about in week 1, right? So the x component of, oh, sorry, it's not a force component, it would be more like a velocity component. Velocity being like a diagonal arrow, like a diagonal vector, and you can split it into the x component and the y component using trigonometry, right?
You might be missing T for the VY, for the displacement.
You're very correct. Thank you. Yep. That, yeah. T there. Okay. All right. So that's projectile motion. Another thing we're going to talk about is relative motion, right? So relative motion is, again, I've been talking about that example of the planes. You know, one's traveling due north, one's traveling due east. There's essentially a way to connect. Not connect. Okay. Basically, you know what? It helps when we see the example. So I'll just leave this here for now, and then we'll come back to it. For curvilinear motion, right? Okay. Basically, we have our curve, and then we have our particle traveling along this curve. You know, its acceleration component, right? It might look something like this. The acceleration could actually be diagonal, but we have a formula that we can use to calculate its tangential acceleration and its normal acceleration, and we can use like Pythagoras theorem to find the magnitude of that diagonal one, right? So these two components, these are its formulas. So the normal one corresponds to that formula. The tangential one corresponds to that formula. So I've done it in the, I guess, like calculus expression, but essentially it's just, if you want to do it in a linear way, it's just that, right? Change in v is over change in t, right? Angular velocity and arc length. I mean, we won't actually see it in this workshop. Helps to come back to it because these will be important formulas for when we do rigid body, rigid body kinematics, right? Okay. Does anyone have any questions with? So I've just done an overview of what we're going to see in this next few questions, right? Okay. So this first one is a projectile motion question, right? Because we've got a projectile being thrown. So of course we're gonna, you know, as our coordinate system is y is positive direction there, x is a positive direction going to the right. So the boy is throwing a ball from point A and is trying to hit the top of the roof, right? It has an initial speed, the ball has an initial speed of VA, which is its diagonal, you know, the diagonal vector for velocity here. Right, so we can split that up into its horizontal component and vertical component, right? Which we'll do first. Determine this angle, right? So this is actually a difficult question. I couldn't find like a simple question, to be honest. Like all the projectile motion questions, at least that I've seen in like the civil school and the mech school from like the workshops, they've been pretty hard. I don't know. I think if you look through like high school textbooks and stuff, you'll be able to find like simpler projectile motion questions to start with, if you like. But yeah, so as soon as you have to find this angle, it becomes a little bit difficult, in my opinion, right? So yeah, it tells you to determine that angle and this max height of C. Sorry. No, my bad. So C is known, like the position of C is 8 meters, right? Because it's hitting the tip of the house. Find the distance D where the boy should stand to make the throw. So basically we have two major unknowns, right, which is that throw angle and that distance away from the house that the boy is located, right? So essentially we're gonna have to do simultaneous equations to solve this, right? So this is like the redrawn diagram. I've called this y final, right? So y final is 8 meters from the ground, so that's the tip of the house. And I've called this yo. Yo is the starting height, right? The datum that I've chosen, which is just a reference point, is the ground, right? Okay, so we need to find an expression for we need to find an expression for theta a, right? So at time equals 0, we can always split our diagonal into its components first. So the diagonal velocity vector, which I'm going to call Vx, right? This is 15. It's 15 cosine, our unknown, right? Right, and we also know that our acceleration in the y direction is negative 9.81 meters per second squared. Right, so that's great. That's our. I mean, I can also write this if I want, which is the acceleration in the x direction is 0, but you don't have to write that because it's implied as well, right? Okay. So we need to create this function for our, we're going to do our vertical motion first, right? Vertical velocity. Right, so the way we do, that, Vt is equal to 15 sine theta a, right, which is our initial portion, right, plus the acceleration, minus 9.81 basically. That's the acceleration in the y direction multiplied by t, right, like that. And at the apex of the throw, let's call it Tc. It's Tc, by the way, sorry, because it's the time it takes to reach that point in the house. We know is 0 meters per second, right? So that's the apex of the throw. So that's kind of like our. Actually, yeah. Okay. Basically, this will give us. How am I going to say this? This is like an initial. Give me 1 second. We're going to sub in v is equal to 0, and then we can find what Tc is, right? We can find the time of when it reaches the top of the house. So I'm just not good at explaining algebra. Okay. So basically, we're copying this part over, right? I'll just show it to you visually. Tc, that's what we're solving for, yeah? And that information plugs in here. You know what I mean? Yeah, okay, good. So when we rearrange for Tc, 15 sine theta a is equal to 9.81, over 9.81. This will be our first equation for our simultaneous equation. Right? Okay. Here's basically what I've written in the formula sheet from earlier, if you want to just plug it into here. Yeah. So this is the displacement in the y direction. It's the y direction. That's 15 sine theta a multiplied by t minus 9.81 over 2 t squared. Yep, so Brad, you were right. That's where the t from earlier was. Okay, so when you plug in Tc, right, we know that the displacement is 7 meters. So it's 7 meters above where it started, essentially, right? It gained a height of 7 meters. You know what I mean? Like, yeah. So 7 is, we're doing the same thing where we're plugging in this this number, right? So I'm just gonna copy this over. Is TC is TC squared, right? And you can imagine here's our second expression for T. So basically what we're gonna do, we're gonna get that box, right? We're gonna use the substitution method, plug that right in, like that. Should give us this. Yeah. We're going to, I think I just, how many steps did I skip? Okay, I'll write the intermediate calc, but yeah. Oh, okay, makes sense. We have one sign here, one sign here. It becomes sine squared, right? Which is what results in that part. 15 times 15 is 225, right? Divided by 9.81. That's what that all is, right? And then minus 4.905 is 9.81 over 2. 15 squared is 225. 9.81 squared is at the bottom of the fraction there, right? And we still have our sine component that's like that, right? Okay, so basically we rearrange for sine squared theta a, right? Which equals that. You can square root both sides. And we basically do sine to the -1 of that, which gives us 51.38 degrees, right? So again, this is not representative of a typical projectile motion question. I just can't find a good one. This is a difficult one, right? Okay, now we can find the horizontal distance d. Horizontal distance d, we can plug back in that equation, right, which we've called 1. Like that. Plug this in, 51.38 degrees, right? Gives us 1.195 seconds, yeah? So that's the time it takes from when he starts to throw to when it reaches the apex, which is also the top of the house, right? Okay, what have I done? I need some more space, so I'm gonna make this smaller. Yeah, sweet. Okay, so that's vertical motion. Vertical motion is the hard part. Horizontal motion is pretty trivial. Basically, the velocity in the x direction is constant, and we remember it's just equal to that initial component the entire time, right? Which now we know is, it was a function of some unknown angle, and since we know the angle now, we can plug it in, get 9.363 meters per second, right? and then sx is just equal to that initial x velocity multiplied by time, right? So yeah, sx, oh yeah, basically we care about this distance d, right? And so we're trying to find this first, right? So this is sx at time is equal to time it reaches, like it takes to reach c, right? So sx, when you plug in, time is equal to tc, which is equal to 1.195 seconds, right? Sorry. We have 9.363 multiplied by that time, right? And we get that that is equal to 11.19 meters. And d, that distance, was simply that number, right? So sx at t is equal to 1.195 seconds minus 4 meters, which gives us 7.19 meters. So it's minus 4 meters because the house, from the center of the house to the edge of the house, is 4 meters, right? Okay. Any questions with that? Okay. It's annoying, but each of the steps hopefully makes sense. Like, it's just a long question. Yeah. Okay. Next we'll do circular motion, and then the last one we'll do will be relative motion, right? So, curvilinear motion, I should say. So, okay, basically the car travels along a curve. The radius is 300 meters, right? If the speed is uniformly increasing from 15 to 27 meters per second in 3 seconds, right? Determine the magnitude of its acceleration at the instant its speed is 20 meters per second, right? That's what we're looking at here, right? Okay, so we know that that radius is 300 meters. That'll be important for when we plug in our formula for the normal normal component of acceleration, right? Okay, and the initial velocity, we were told here, was 15 meters per second, and it increases to 27 meters per second, right? Okay, so now we have all the pieces we need. So yeah, we literally just plug in basically this v, which we plug in, right? Okay, how do I say this? So we're basically increasing from 15 meters per second up to 27 meters per second, right? The value we plug in for the value we plug in for v is going to be 20, because that's the snapshot in time we care about, right? It's at this unknown time at the moment, right? So we're going to plug in 20 squared over this radius, right? And this will be our normal acceleration, which is also called our centripetal acceleration, right?
Yeah.
That's 1.33 meters per second squared. And then for our tangential component, remember, if we're talking about a linear acceleration, right? It's change in v over change in t. We need 2 points, right, when we do delta v. So we're going to take these 2 points here, right? Because we don't know this, right? So this would be an unknown amount of time. I mean, we can calculate it, but it's annoying. But we do know that delta t here is 3 seconds. Exclamation mark. So we're going to take those two values, right? Because that will give us the correct slope, right? So it's going to be 27 minus 15 over 3 seconds, right? Tangential acceleration. Yeah, anyway, that's the, tangential acceleration is basically this component, and then normal acceleration is how much it wants to accelerate towards the middle of the circle, right? And then the overall magnitude of acceleration is going to be this diagonal kind of vector, like that, right? Everyone following? Maybe? Yeah, no? Okay. So what we're going to do is calculate exactly that, which is that diagonal component, right? Oh, you know what? I might... Did I ask for the angle? It didn't actually ask for the angle, but for some reason I've decided to do the angle. Okay. I'll draw it out. If we're looking at the acceleration components, AT goes this way, AN goes towards the middle of the circle, right? And then what we're finding, which is A, right, overall, the net acceleration, it's going to be diagonal, and we'll take this as that angle, right? So this is angle away from the tangent. So that's going to be 1.33 and 4, and this we're going to utilize Pythagoras and vectors and stuff like that to find that magnitude. So that's the answer. But for some reason, I've also decided to include the angle. I don't know. So yeah, if you're curious what that angle is, it's that. So that angle is that. Yep. Okay. Everyone okay with that kind of concept? Yep. I feel like half of this course is maths. Oh, sorry, half of the dynamics portion of this course is maths. The other half is understanding kind of like the hierarchy of, you know, particles, rigid bodies, kinematics, kinetics. It helps you understand what the question's asking for, how to solve it. So if you can kind of look at a question and understand the rough steps, that's the first step basically when you're solving dynamics questions. And then the next step is looking through a formula sheet to find which formula is most appropriate essentially. So because it's a very like broad part of the course, right, there's gonna be a lot of formulas and you're gonna get overwhelmed. You're not gonna know which ones to use unless you can kind of at least categorize what the questions are. That's why I'm going through so much effort to explain, you know, okay, this is a curvilinear question and what it looks like. Okay, this is a, you know, relative motion question, right? Because it's going to help you a lot in the midterm. And then, you know, starting from next week as well, you're going to have to consider, okay, when do I have to use the work energy methods? When am I going to have to use the impulse momentum methods? You know, like this is a lot, but yeah, I'm going to try to cover all the bases basically, and then hopefully you shouldn't be surprised when you see it could be any number of questions, like any number of types of questions in your paper. So hopefully, yeah, you're not overwhelmed when you look at your paper basically. I remember the first time I taught 1300, it was in you know, term 2, like this time last year. And like I feel like I didn't explain the dynamics very well, and people were literally asking me, are we looking at it like top down, or are we looking at it like side on? I'm like, fuck, okay, I didn't do my job properly basically, because the first thing you should do is be able to identify what coordinates we're talking about for, like, you know, are we talking about the wider dimension where it has like gravity involved? Are we talking about, you know, billiard balls where it's top down? Like a lot of these things are just implied, you know what I mean? Yeah, anyway. Sorry, I just started ranting for no reason. Okay, so we have two cars here. Car A is this one on the left, It travels due east at a constant speed of 36 kilometers per hour. Car B starts from rest, that's car B there, and accelerates south at 1.2 meters per second squared. What is the relative motion, velocity and acceleration of car B with respect to A 5 seconds after car B starts accelerating? Okay, so just looking at these two and these numbers that you can see, what's the first thing you should do? Very good. You should definitely convert away from kilometers per hour into SI units. So in the dynamics portion of the course, we're going to be using, meters, seconds, newtons, whatever. SI units, right? In statics, we used like kilonewtons and meters, and you probably didn't see kPa, but this was for beams. And then in your space gas modeling assignment, you probably saw like MPa, millimeters, Newton, millimeters, all that stuff, right? But yeah, we just deal with SI units for dynamics, right? There's one question I saw and it like annoyed me. It was from a textbook and they used like pound inches and I'm not dealing with that shit. I skipped the question. Anyway. Yeah, so convert VA into SI units basically, right? So the way you can do this, I'll do it once and then we won't have to see this conversion again. Basically, you want to think about it like, okay, 1 meter per second is, yeah, I'll just show you the conversion. It's basically this, these units cancel out, so you divide it by 3.6, right? You either times by 3.6 or divide by 3.6 when you're doing this conversion, and you have to think about it logically, right? So if we're going like, say you're driving in a car, you're going 40 kilometers an hour in a school zone, right? If you times it by 3.6 to get meters per second, you're gonna be going like over 100 meters per second, you know what I mean, in a school zone. That's just not how it works. So in that case, you think about it logically how the numbers work, and you just divide it by 3.6, you know what I mean? And then vice versa for the other conversion. Okay, so I'm going to start using I, J, and K. I think I might have briefly gone over this in week 1's workshop, but these are the unit vectors, right? So, here I've drawn them. So in the wider, did I do it the wrong way? That looks like the wrong way. Yeah, fuck, okay, my bad. So I is the one that corresponds to the X direction, right? J is the one that corresponds in the Y direction. And that's what we're going to roll with. So I want to express it in terms of, of unit vectors, right? So I'm going to leave it like that. Okay, step 2, we're going to still use that idea of function is equal to the initial value and then the change over time, essentially, right? So car B, right? Car B is this one. It starts from rest, right? We're told that car B starts from rest. So this is going to start at 0, and its acceleration over time was negative 1.2 J. So this is relevant because J is positive that way, and it's moving downwards, right? So it's going to be a negative J, that right? So VB is equal to negative 1.2 T J. Right, so that's its function. So we've got an expression for A and we have an expression for B's velocity as well now, right? So we want to find the relative velocity, right? And yeah, not only that, we want to find the relative acceleration, and we want to find what the values are at time is equal to 5 seconds, right? So 5 seconds after the car starts moving, right? So basically, we have this, let me just copy this over. Yeah, we sub in time is equal to 5 seconds, and then we get negative 6j, right? So this is the velocity at 5 seconds for B. And then for A, I mean A is just this. A is always constant. A is always constant, so it was 10 going to the right. Let me erase this. Okay, here's the way you think about it, right? You draw VA and you draw VB as a vector diagram, and they're both originating from the same point, right? So VB is this one, and it's going down, right? And then VA is going to the right, and I like to draw them to scale relatively, like that. Yep. And then basically, if we want an expression of, what did it say? Velocity of B relative to A, right? That's VB slash A. We have to do this, right? This is the velocity of B relative to A. It's basically, imagine you're the car that's driving on the path of A. The velocity of B looks like it's going down, right? And it's looking like it's going to the left. Do you know what I mean? That's the way that you think about it. So then at that point, yeah, that's where B is, right? Okay, basically, there's a formula for VBA, right? So VBA, sorry, velocity of B relative to A. Okay. Here's how I think about it, right? Tip to tail arrows, right? Like that, right? So velocity of B, which is this arrow on the left, is equal to if you travel the distance of VA and you add on the distance of VBA, right? Yeah? Okay, now we're going to rearrange for VBA. And it's going to be VB minus VA. So that's another expression, right? So basically, we're going to sub in this value for VB. And we're going to sub in this value for VA. So the reason why I've done it in terms of unit vectors is because they're not going in the same dimension, right? You can't subtract the numbers directly. You have to subtract them as if they're vectors, right? So you have a vector in the j direction, you have a vector in the I direction. So now we have an accurate expression for this, right? So VBA is equal to negative 10I minus 6J. And that's in meters per second. Okay, that's our answer. Right, that. Okay. And the acceleration of, okay. If we look at our question again, right? A is a car that's traveling at a constant speed, so it's not accelerating, right? B is a car that's accelerating, but starts off at 0 speed or whatever, but it still has that constant acceleration, right? So how these arrows look in terms of relative acceleration, it's like this. Okay, I might. Oh, fuck, sure. This is V, okay, these arrows are inaccurate, right? But what I'm trying to tell you is because this is 0, right? It's not accelerating. Then the tip to tail is like that, right? So these are equal, right? So acceleration of B is equal to acceleration of A plus acceleration of B relative to A, but acceleration of A is 0, So acceleration of b relative to a is simply going to be just this one, right? Which is that. So it looks like that. Oops. Okay. Does anyone have any questions? So the relative, I want to say the relative velocity topic, like it could be in your midterm, but more or less it's just setting up, like what I've just been talking about in this question. It's more or less setting up for rigid body kinematics. So when we do this really hard topic towards the end of the course in week 10, we need to know relative motion, right? This one. This like depends on relative motion, right? So it's really good to try to get it down, at least for that part of the course. But more or less, in your midterm, you can probably expect a projectile motion question. You can expect a rectilinear motion question. They might chuck you a curvilinear motion question. What happened was none of the midterms before last year had curvilinear motion, and then it had curvilinear motion in last year's midterm, and then they were like, fuck. It's kind of like how in your midterm for statics, they chucked in that random question from the week 2 workshop as like that first question. They did a mix-up last year, basically. So hopefully this year they're a bit nicer for the dynamics portion, dynamics quiz or whatever, because last year was really hard. But anyway, sorry, I don't mean to scare you, but anyway, that's the end of the workshop. And yeah, come up in front if you have a question.